Hello everybody, my name is Jordi Coll and I'm one of the authors of this paper titled Combining Close Learning and Branch and Bound for MaxSAT. First of all, on behalf of all the authors, I would like to thank to the organization of CP2021 for the organization of the conference, as well as for this Best Paper Award. So in this talk, I will present our new branch and bound MaxSAT solver, which is called MaxCDCL. I will start giving some preliminaries on MaxSAT and on branch and bound. Then I will present the solver, and finally I will present some results and conclusions. So MaxSAT is the optimization version of the well-known Boolean satisfiability problem, SAT. And MaxSAT is a trendy research topic, with an annual MaxSAT evaluations where the best MaxSAT solvers compete. And in particular in this work we focus in partial MaxSAT. Partial MaxSAT is the problem of finding an assignment for a set of propositional variables such that all the hard clauses of a set are satisfied, and we maximize the number of satisfied soft clauses, or what is the same, we minimize the number of unsatisfied soft clauses. Here we have an example of a partial MaxSAT formula. We have 3 hard clauses, so we have a conjunction of 3 clauses, and every clause is a disjunction of 2 literals. And we also have in this case 4 soft clauses. A possible solution for this formula is this one. We assign x to false, y to true, and z to true. We can observe that all the hard clauses are satisfied because there is one true literal in every clause, and there is just one soft clause that is falsified, this one here, because it has no literal that is true. And since there is one soft clause that is falsified, the cost is 1. This is in fact an optimal solution for this formula. Before solving the formula, we will perform a process that consists in expressing soft clauses as soft literals. This means that any non-unary soft clause, like this one here, will be replaced by a new auxiliary literal. In the example here, we replace this clause here by this auxiliary literal p, and in order to do that, we have to add hard clauses stating this equivalence. That is, that the new literal is equivalent to the soft clause that it replaces. Therefore, we have now only unary soft clauses, and we will name them soft literals. This way, the problem now can be stated as: find an assignment that satisfies all the hard clauses again, and that minimize the number of soft literals that are assigned false. There are many possible ways to classify MaxSAT solvers. We could say that all the state-of-the-art MaxSAT solvers are SAT-based, in the sense that they translate the MaxSAT problem into a series of satisfiability calls, and then they perform different algorithms to achieve optimization. We have minimum hitting set MaxSAT solvers, we have model-based MaxSAT solvers, and core-based. On the other hand, we have branch and bound MaxSAT solvers. A very important difference with respect to SAT-based solvers is that branch and bound MaxSAT solvers do not have close learning. These solvers are well suited for random and some crafted instances, but on the other hand, they have shown poor performance on industrial instances. And probably because of that, we can observe that branch and bound MaxSAT solvers have not been present in MaxSAT evaluations since the year 2017. This can be observed in this table here. Here we include the MaxSAT solvers that participated in editions 2019 and 2020 of the MaxSAT evaluation, and none of them used branch and bound. And in fact, in order to find the last branch and bound MaxSAT solver, we have to go to year 2016 with MaxSAT. So there is a prevailing opinion in the field that branch and bound MaxSAT solvers are not competitive for industrial instances. But in this work, we show that, in fact, branch and bound MaxSAT can be made competitive for industrial MaxSAT, and we achieve that by integrating close learning into a branch and bound MaxSAT solver. So branch and bound is a well-known technique to solve hard optimization problems. It consists on exploring a search tree, looking for optimal solutions, Every time we find a solution, we record what is the cost of this solution that we have found, and we set this as an upper bound of the cost. So if we find a new solution with a better cost, like this in this branch here, we can improve this upper bound, and in any node of the search tree, if we see that the cost of the partial solution so far is greater or equal than the upper bound, we can prune the branch of the search tree because the best solution so far cannot be improved. In fact, we can do better, and at every node of the search tree, we can underestimate a lower bound of the cost. That is, we can underestimate what will be the cost of any possible extension of the partial assignment so far. And if this lower bound reaches the upper bound, we can prune the branch of the search tree. So in our solver MaxCDCL, we use unit propagation to compute this underestimated lower bound. This technique is not new. Other BnB MaxSAT solvers have been using unit propagation to underestimate the lower bound. But what is new is that when we detect that lower bound reaches the upper bound, we pruned this search tree using close learning. In fact, what we will do is detecting an implied clause that is falsified, and then this clause is analyzed in order to make a backtrack or a back jump as a SAT solver, a CDCL SAT solver would do. So I will explain this method to underestimate the lower bound that is based on unit propagation. I will explain that with an example. Suppose we have this partial MaxSAT formula here. There are 4 hard clauses, and we have 3 soft literals, y1, 2, and 3. And we start with the partial assignment x2, x4. And the first thing we will do is assign some of these soft literals, that is unassigned. We start with y1. And now we can observe that this clause here has become unit. This means that all the literals of the clause are falsified except one, that is this literal x1, that is unassigned. Then the unit propagation rule says that in this case we can propagate this literal to true. So we apply unit propagation and we do that. And then we can observe that another clause has become unit. Now we can propagate not x3 with unit propagation. And this process is repeated until we detect one of these two situations. Either a hard clause is falsified, or some soft literal is falsified, is propagated to false. This second case will happen now, because now we have this unit clause, and literal y2 will be propagated to false. So in this case, and in any of these two cases, what we detect is a set of soft literals that cannot be true at the same time. In this case, we have detected that y1 and y2 cannot be true at the same time. And this is what we call an unsatisfiability core. This means that at least one of these two literals must be false. Therefore, we can increase the lower bound by 1, because at least one of them will be false. So what we will do in this process to underestimate the lower bound is compute disjoint cores, and for every core that we find, we will increase the lower bound by 1. In particular, notice that this core that we have found is implied by a partial assignment. In this example, this core is implied by x2 and x4, and therefore we will say that it is a local core. So the whole process to prune the search tree works as follows. As we have shown, we will obtain local cores, and for every local core that we obtain, first of all, we will minimize it in order to obtain a minimum set of soft literals that is a local core, and we will also obtain the reasons for this local core. We will compute many local cores, and every time we detect that the lower bound reaches the upper bound, we will raise what we call a soft conflict. This situation will be soft conflict, and in this case we will obtain a clause that is implied by the hard clauses and by this upper bound that we have, and this clause will be falsified by the current partial assignment. This clause will be obtained from the reasons of the course, and then this falsified clause can be analyzed as any conflict-driven closed learning set solver would do, for instance using the first unique implication point scheme, and we will be able to learn a lemma that will prevent having the same conflict in the future, and we can backtrack or backjump and continue with the search. So now I will explain the full process of detecting a soft conflict with an example. Suppose we are given an upper bound of 3, these 7 soft literals from y1 to y7, and we have this partial assignment. Note that y7, that is a soft literal, is false, and therefore the lower bound is already 1. In order to explain this example in a common framework, we will say that we have already detected one local core, that is y7, and the reason for this core is that y7 is false. And we start the look-ahead procedure. We do a first iteration, we assign y1, and by applying unit propagation, we propagate node y3. In fact, this generates an implication graph like this one, and this is analyzed. I will not explain the details now, but analyzing the implication graph, we can check that the obtained local core is y1, y3, and that the reasons for this core are x2 and x4. So we add one extra core in our set of cores, and we increase the lower bound by 1, and we update the set of reasons for all the cores. And we continue with a second iteration. Now we have assigned, for instance, y2, y4, and y5. Again, analyzing the implication graph, we have detected now that the minimized local core is y2, y5. So in this case, y4 is not relevant for this core. And we have also detected that the reasons are x2 and x5. So we add one extra core, we update the set of reasons, and now we have detected that the lower bound is equal to the upper bound. Therefore, we have detected a soft conflict. This conflict can be explained by this clause here. This clause was not existing, but this is a clause that is a logic consequence of the hard clauses of the formula and the upper bound that we have. This conflicting clause is composed of the negations of the reasons, and this clause is falsified given the partial assignment that we have. Therefore, this clause can be analyzed with the standard techniques of SAT solving. For instance, we can search the first unique implication point, and this will let us backjump and continue the search as any SAT solver would do. Another feature that we include in our solver is hardening. The idea behind hardening is that when the lower bound is equal to the upper bound minus 1, we know that we cannot afford setting more soft literals to false. Otherwise, we would reach the upper bound. So following the same example as before, but now with an upper bound of 4, this is the case. So hardening can be applied. What we can do is take all the soft literals that are unassigned and do not belong to any core, and we will propagate them to true. So hardening is not new. In fact, other branch and bound MaxSAT solvers already use hardening. But what is new is that we apply hardening by introducing new clauses. So for each literal that we want to propagate to true, we add one extra clause. This clause contains the negations of the reasons and the literal that we want to propagate. In this case, y4 and y6. And note that, given the partial assignment, this clause is unit. Therefore, unit propagation will propagate these two literals to true. And hence, we satisfy a CDCL invariant, that is that every assigned literal is either decided or it has been unit propagated. Notice that the look-ahead method to underestimate the lower bound has some potential drawbacks. Running look-ahead at every node of the search tree is too much time-consuming, and moreover, there is no guarantee that every time that we run look-ahead, we detect a soft conflict. Therefore, in our solver, we implement a bounding procedure to try to reduce the number of unsuccessful look-aheads. So, with probability 0.01, we will always run look-ahead for probing purpose, and from the runs we will record the average and the standard deviation of the number of cores that we detected. But only in successful look-aheads This means look-aheads that detected a soft conflict. Then, for the other cases out of this probability, we compute this value k, that is the number of cores that are needed to detect a soft conflict in the current look-ahead, that is the difference between the upper bound and the number of falsified soft literals by the partial assignment. And then look-ahead will be skipped if this value k is greater than the average plus the standard deviation times a coefficient. And this coefficient here is a value that we dynamically adjust to try to get a success rate between 0.6 and 0.75. So summing up, the algorithm that our solver implements is a generalization of the CDCL algorithm that current set solvers implement. I will not explain all the algorithm in detail, but I will just highlight the differences that make it a generalization. And these differences are highlighted in color blue. So, the first difference that we can observe is that this algorithm is not only for solving a set of hard clauses, but we also want that the solution has a cost smaller than a given upper bound. And if we find a solution, we will not just say that the formula is satisfiable, but we will say what is the cost of the solution that we have found. And also, another basic difference is that when we detect conflicts, they can not only be hard conflicts, that would be falsifying a hard clause, but they can also be soft conflicts that are detected using the look-ahead method that I have presented. And finally, another difference is that we include the hardening procedure that we have explained. For the evaluation of our solver, we consider the two following datasets. On one hand, we consider the union of all the instances from MaxSAT evaluations years 2019 and 2020. This is a total of 1000 instances. And on the other hand, we consider a subset of the master collection that contains all the instances from MaxSAT evaluations. We take instances from all the families, but we take at most 100 instances per family. This is a total of 3614 instances. And in every experiment, we use the same cutoff that is used in MaxSAT evaluations, that is 1 hour. So in this first experiment, we analyze the different features that are included in our solver. The last row is the full solver with all the features, and we can see that in this first set we solve 734 instances, and in this other set 3022 instances. And then in each row we analyze what happens if we individually remove some feature. So for instance, if we do not use look-ahead to look for local cores and detect soft conflicts, the number of solved instances is 505. If we do not use hardening, we solve 664. And if we always run look-ahead, so we do not use the probing strategy to try to avoid unsuccessful look-aheads, the number of solved is 681. These two other features, I have not explained them in detail in this presentation, but basically in the paper we also show that it is important the order that we choose to pick the soft literals when running the look-ahead procedure to find local cores. And we also show that it improves the performance to update the VSIDS scores of the variables that appear into detected local cores. So this score is used for the heuristic of the set solver to make decisions. In this second table, we show a comparison of our solver with the best 5 solvers of the MaxSAT evaluation 2020. We can see that in this first dataset, our solver is the 4th in number of solved instances, and in this other set is the second one, the second best. We can also see here that MaxCDCL is able to solve an important number of instances that no other solvers can solve. For instance, this cell here is saying that MaxCDCL was able to solve 36 instances that MaxHS was not able to solve. Also, this column here says what is the number of instances that only the solver in the row was able to solve. So, for instance, in this set there were 16 instances that only MaxCDCL was able to solve. None of the other solvers could solve any of these instances. And this number is still more impressive, 67 for the master collection dataset. Also, that MaxCDCL is useful to solve new kind of instances can be seen in this experiment. Here we construct portfolio solvers by combining pairwise two solvers, the different solvers we have considered in the last experiments. And for each combination, we let each one of the two solvers to run for half an hour. So combining MaxCDCL and MaxHH, for instance, let us solve 785 instances. So we can observe that the best combinations in this dataset contain MaxCDCL, are in fact a combination with MaxHH, eval MaxSAT, and RC2. And this result is still more important for the master collection because we can see that any combination that contains MaxCDCL is better than any other combination that does not contain MaxCDCL. And finally, in this last table, we compare our solver with another existing branch-and-bound MaxSAT solver. It is MaxSAT that won many tracks in the last MaxSAT evaluation where branch-and-bound MaxSAT solve participated, was year 2016. And in that edition, there were specific tracks for MaxSAT and partial MaxSAT, and for random, crafted, and industrial instances. What we can observe is that MaxCDCL is better at solving instances from the industrial tracks. This row here, 37 compared to 0, and this row here, 512 compared to 183, and also is much better for the dataset of the last evaluations. On the other hand, MaxSAT is better at solving some random and crafted instances, as we can observe, for instance, here. And this is because MaxSAT makes a more intensive use of bounding techniques. So, concluding, in this work we have presented our new branch-and-bound MaxSAT solver MaxCDCL that combines branch-and-bound and closed learning. The algorithm that our solver implements is a generalization of CDCL, and our solver is ranked among the top 5 solvers, considering solvers of the last evaluations. We have also shown, contrarily to what is the prevailing opinion in the field, that branch-and-bound can be made effective for industrial MaxSAT instances, and also that this technique has potential to solve new kind of instances that other state-of-the-art MaxSAT solvers cannot solve. In the future work, we consider to implement the weighted version of MaxCDCL to solve weighted MaxSAT, and this approach that we use could also be adapted to other problems such as pseudo-volume optimization or weighted CSPs. Thank you very much for your attention, and we will be very happy to answer any questions you may have.